Today is the 21st day of the May LeetCode 30-day challenge, and the problem will be count square submatrix with all ones. So we are given a matrix of m times n size of all ones and zeros, and we are asked to return how many square submatrices have all ones. For example, in the first example, the result will be 15 because there are 10 squares of size 1 by 1 and 4 of them are 2 by 2. And 1 of them are 3 by 3, which is obviously you can see from this here, and the total result will be 15. So how do we solve this problem? The problem can be solved via dynamic programming, and which result in time space of O m times n and space of O1 if we did not count the matrix as input space complexity. And before I go into explain this problem, I will use a lot of the idea in problem 221 maximal square. So before you continue watch this video, I highly suggest you practice maximal square or watch my dedicated video of the 27th day of the April LeetCode 30-day challenge, which I have made an explanation video of how to solve problem 221 maximal square. And after you understanding how to solve the maximal square, then solving this count square submatrix with all ones will be a piece of cake. And now I will jump to the explanation of today's problem. Let's go. So as you can see, this is very similar to that of the explanation in problem 221 maximal square. And basically this problem can also be divided into 4 types of the subproblem. Oh, sorry, this is one. And the first one is we are all consider the square matrix containing size of 3 by 3, and the first one you can see that we only talk about when we are reaching the bottom right part. So you can see that if we reach the bottom right part, then in the first situation, say this one, the result will be plus by 3. Why the result will be incremented by 3? Because you are basically increment the result. Basically you have found the square of size 1 by 1, and there is another square of size 2 by 2 which can be also formed, and the square size of 3 by 3 which can be also formed when the bottom right part is 1, and then the result will increment by 3. How do we get 3? Actually, we can get 3 from its neighbor, and its neighbor will be defined at the top left, and then we will choose the minimal from them and plus 1 to get our answer, and then jump to the second subproblem. The second subproblem is very similar to the first, just the top right, this part, or this part, the right top part or the bottom left part will containing 1 0, which will not make them continuous. So the result will only be incremented by 2, as you can see from here, because we take the minimum of 3, and minimum of 3 is 1, and 1 plus 1 is 2, so the result will increment by 2. And definitely yes, because at the bottom right part, you can see that here we form a square of 1 by 1, and as we expand, there is another square we can form which is size 2 by 2. However, for the size 3 by 3 we cannot form, and this is 1. So I will draw 1 here. Okay, and the third subproblem is very similar idea to the before. So At here, we take the minimum of its neighbor, which is 1, and 1 plus 1, we get 2. Obviously, you can see that if we reach to the bottom right part, then this square size of 1 by 1 can be formed. And it can also be expanded to the square size of 2 by 2. And so, the overall result will increment by 2. And for the last subproblem, and here we still take the neighbor, the minimum of the neighbor, which is 0, and 0 plus 1 get 1. As you can see here, we can only form the size of square of 1 by 1, and for the square of 2 by 2, we cannot form. So, that's how we solve this problem. And why is dynamic programming applicable here? Because we have the optimal substructure. Why? As you can see from each substructure, this substructure, we will take the neighbors, we will choose the minimum from the neighbors, and that is the overall best result from the neighbors, and we will take them out and to form our new answer, which guarantee the characteristic of the optimal substructure. And for the if we want to check the overlapping subproblems, definitely, because I have divided this problem into 4 subproblems to discuss. So the second characteristic definitely exists. And now I will jump to the coding part. So coding of this problem is very similar to that of the problem 221, maximal square. So we first get a row, and column, the top right part, and minimum of the top and left, and then plus 1 for the new answer. And finally return result. And let's see if this works. Okay, get accepted, and thank you for watching today's video. See you tomorrow. Bye bye.